circuit below begins with the switch in the open position and the capacitor carrying zero charge. The battery has a voltage of 10 volts, the resistor is 5 kiloohms, and the capacitor is 12 microfarads. At time t equals 0, the switch in the circuit is closed, and then we are asked to find a variety of answers. This problem falls under the general category of a transient response, or what happens immediately following a sudden change, such as a switch closure. For these type of problems, we're going to use a two-step procedure. One step is reasoning and one step is recognition. Let's work for a moment on the recognition step. In mathematics, we're frequently presented with a Cartesian coordinate system of y versus x, and one of the earliest mathematical forms that each of us is taught is the form of a straight line. Now, the way I would like to discuss these straight lines is to recognize that each one of these straight lines, even though they are all different from one another, follow exactly the same formula of y equals mx plus b. The thing that distinguishes one straight line from another is the value of m and the value of b. Sometime long before taking your college physics course, you were taught the process to determine any straight line's equation by using aspects of that straight line to determine m, to determine b, and then you got the formula itself by plugging into the well-known form. Today we're going to introduce two more mathematical forms that have the same characteristic. Each one of these forms is a function of two constants, and when we see these, the process of determining the two constants will allow us to specify the equation in detail. The one on the left is called a saturating exponential, and the one on the right is called a falling exponential. All of the transient problems that we'll be encountering in this class have quantities that are either described by the saturating exponential or the falling exponential, and our job is to be able to recognize the constants associated with these two functions. The function for the saturating exponential is that the y coordinate is some amplitude times 1 minus e to the negative t over some characteristic time tau. You could just as easily have written these y as a function of x, but in this case we're writing y as a function of t since that's most similar to what we're doing. Similarly, the y versus t for a falling exponential also has an amplitude, e to the minus t over some characteristic time, and our process is simply being able to identify the two constants, amplitude and t, in each one of these formulas. For the saturating exponential, you can see that asymptotically the function itself approaches some value. That value is the constant a. In the case of the falling exponential, you asymptotically approach 0, having begun at the value a. So by simple inspection, we can deduce the a in each one of these forms. The tau, or time constant, is a little bit trickier because in fact the function itself is featureless and smooth along the x-axis. However, if you look at the two forms mathematically, you can see that tau in each case has a common interpretation, and tau in each case occurs at the time when you only have 1/8 of the way left to reach the asymptotic value. 1/8 sounds like a funny number, but we know that 1/3 is 1 over 3 and 1/4 is 1 over 4, so 1/8 is 1 over e. And if you plug in the numbers, that's about 37%. So when you have only 37% of the way left to your asymptotic value, that's the time tau in each one of these figures. Armed with these two equations and the recognition that one or the other represents the solution to all of the transient problems in this class, we will be able, by reasoning the shape of the curve of any quantity y, produce that equation which describes the quantity as a function of time, and this will be necessary to solve the transient. Going back to the problem at hand, part A asks us to determine the time constant. This is something we know from memory. The time constant of an RC circuit is resistance times capacitance, and we will have 5 kiloohms times 12 microfarads. 12 times 5 is 60, and kilo times micro is milli. So the result of this calculation is that the circuit shown in the diagram has a time constant of 60 milliseconds. The problem at hand has two circuit elements in it. One is a resistor, and we know that the voltage on the resistor is current times resistance, and the other element is a capacitor, and we know that the voltage on a capacitor capacitor is charge over capacitance. Therefore, we recognize that since R and C are simply constants, there are four quantities that we would like to understand the time dependence of in order to understand everything that happens in this circuit following the transient. These four quantities are the two voltages VR, VC, and the current and charge. In order to organize these columns, we're going to put the capacitor on the right. Its condition is specified by knowing its voltage and charge at any moment. And we'll put the resistor on the left, and to specify a resistor, we would like to know the resistor's voltage and current. We're going to begin our reasoning by the recognition that the capacitor begins with zero charge. Since the voltage on the capacitor is proportional to the charge, if you don't have any charge, you don't have any voltage on the capacitor either. Next, remaining at time equals 0, we recognize that after the switch is closed, the sum of the voltage on the resistor and the voltage on the capacitor must add up to the battery, which is a total of 10. So if the capacitor hasn't got any, the resistor has got the remainder and begins at 10 volts. Next, the connection between the voltage on the resistor and its current is that V equals IR. So we need to take our 10 volts and divide by 5 kiloohms. 10 over 5 is 2, and 1 over kilo is milli, so the current must begin at 2 milliamps. As a result of the current flow, the capacitor's charge will increase. This means that the capacitor's voltage will increase. This means that the leftover added up to 10 is smaller, so the voltage on the resistor will decrease, as will the current on the resistor. At this moment, there is still current, not as much as before, so the charge on the capacitor will rise again, but less quickly. Same thing for the voltage on the capacitor. The voltage on the resistor falls but less quickly, and the current through the resistor falls but less quickly. We can already see each of our four families beginning to form, and so we can write them out in their entirety, saturating exponentials for the voltage on the capacitor and the charge on the capacitor, and falling exponentials for the voltage and current through the resistor. For these sketches to be complete, we need numerical values on the y-axis. We already have that for the resistor, but we haven't completed that for the capacitor. We recognize that the terminating condition of this circuit is that the voltage on the resistor is 0, meaning that the capacitor has all 10 volts. Finally, we use the relationship that V on a capacitor is Q over C, so that the charge is voltage times capacitance. 10 volts times 12 microfarads, 10 times 12 is 120 microcoulombs. And this completes the four sketches that have been made simply by out-reasoning the problem and not with a lot of complicated mathematics, and certainly without memorization. It's now a simple task to find the time dependencies of all four quantities, and we're going to write these equations stacked in the same configuration as the sketch to make things easier. We see that the amplitude for the voltage on the resistor is 10 volts, and it's a falling exponential, so it's simply 10 times e to the minus t over tau. The amplitude of the current is 2 milliamps, also e to the minus t over tau. The voltage on the capacitor and its charge are both formed as saturating exponentials. The amplitude for the saturating exponential of the voltage on the capacitor is 10 volts, and the amplitude for the saturating charge is 120 microcoulombs. Notice that I didn't draw units with the number 10 because they were in volts. However, for the 2 milliamps and 120 microcoulombs, I was careful to write the units so as to not lose track of either the milli or the micro. Finally, in part D of this problem, we are asked at what time. To answer that, we will simply specify a value for t, and this is an ill-formed question. We are asked for the time at which voltage on the capacitor equals 3. The solution to this question can be found simply by finding a relationship between the voltage on the capacitor and time. That relationship is here, and so we're able to plug in that 3 volts should equal to 10 times the quantity 1 minus e to the negative t over tau. Before we even solve this algebraically, let's put a little thought into the problem. We know that at t equals tau, 60 milliseconds, there will only be 1/8 of the way to go to 10. That would mean we're around 7 volts. Well, we haven't gotten there. We've only gotten to 3 volts. Therefore, our expectation is that the time we get as a solution is going to be less than tau by more than a factor of 2. After a couple of steps of algebra, we're able to see that the time in question is going to be equal to negative the time constant tau times the natural log of 0.7. The result of this calculation is that t equals 21.4 milliseconds, which is not only correct, it also matches our expectation that we should be significantly less than the time tau, which was 60 milliseconds. And that completes our analysis of the transient for charging up a capacitor. Don't forget to review on your own the transient analysis of discharging a capacitor, in which all quantities in the system are falling exponentials, no rising exponentials at all.